Okay, so stepping into the world of serious manufacturing equipment,
Yeah,
especially when you're looking at machinery that needs to handle, massive parts or just really brutal materials, it can feel like, well, like trying to learn a new language overnight.
it really can.
Deciding between different types of machines, like picking the right CNC lathe for a truly demanding job, that can be genuinely overwhelming.
Mm-hmm.
That's exactly why we're diving into this today. We've pulled together a whole stack of sources, articles, research notes, basically trying to extract the most important nuggets of knowledge.
Yeah, there's a lot out there.
Right. So our mission here is really to give you a shortcut, help you get well informed, highlighting what truly matters when you're trying to figure out these core differences between heavy duty and standard CNC lathes.
And it's actually more than just avoiding that overwhelmed feeling, isn't it?
Yeah,
I mean, getting this decision right is absolutely fundamental.
absolutely.
It impacts everything. How efficiently you use your time, the costs you incur, and critically, the kind of work you're actually capable of taking on in your shop. It sets your ceiling, in a way.
That's a great way to put it. Okay, so let's unpack this then. When we peel back the layers, look at a heavy-duty CNC lathe compared to a standard one.
Yeah.
What's the absolute foundation? What makes it fundamentally different in its actual construction?
Well, what's fascinating here, and it came through in the reading, is how the design philosophy just diverges right from the start. A heavy-duty machine isn't simply scaled up.
Okay.
It's engineered for a completely different level of stress. These machines, they're built with significantly larger, much more rigid structures. They use more robust, often frankly oversized components compared to standard ones.
Oversized.
Yeah. And this fundamental difference in the build, that's what enables them to handle not just large parts, but incredibly heavy work pieces. And to perform these really aggressive, high-force cutting operations that, well, a standard lathe just isn't designed to withstand. It would deflect or worse.
Okay, yeah. That inherent rigidity makes total sense when you're talking about wrestling with big, heavy parts. But then the sources really pivot to discussing the spindles, specifically power and torque. They make a point that it's not just a simple more is better situation. What did the research reveal as the crucial distinction there?
Yeah, this raises a really important question. What are you actually trying to do with that spindle power?
Right.
The material highlights that heavy-duty lathes, they prioritize high torque, especially at lower speeds.
Ah, okay. Lower speeds.
Exactly. And this capability, which is backed by substantial power, of course, is essential for effectively cutting large, tough materials.
Yeah.
You need that grunt to avoid stalling the tool
Mm,
or having the whole machine vibrate excessively.
makes sense.
The sources give some pretty compelling numbers, actually. Spindle motors, they frequently range from 30 kilowatts up to 55 kilowatts, sometimes even higher.
Yeah.
And they're capable of achieving several thousand Newton meters of torque, particularly when running slower at those lower RPMs. You'll see features built specifically for this purpose, things like large spindle bores, heavy-duty bearings designed for just immense cutting forces, and often advanced cooling systems like oil cooling to manage the heat from those sustained heavy cuts.
Okay.
Now, you contrast that with standard CNC lathes. They're typically optimized for higher spindle speeds, but with more moderate torque and power.
Right. Speed focus.
Exactly. Their design supports faster machining of smaller parts, maybe achieving finer surface finishes more efficiently. One article gave an example power range. I think it was around 5.5 kilowatts for certain applications, so a big difference.
Huge difference.
And the material you're cutting is absolutely key here. High-strength alloys demand that high torque, whereas something like aluminum, you can machine that very efficiently at high speeds with much lower torque.
Ah, that clicks. So the key insight isn't just more power overall, it's how that power translates into torque, specifically at the speeds you need for the material you're cutting. It's kind of like having the grunt of a bulldozer in low gear versus the speed of a race car, maybe.
That's a great analogy. Yeah,
Both powerful, but built for entirely different jobs.
precisely.
Okay, so circling back to that structure you mentioned earlier, the sources repeatedly emphasized the bed and the guideways as being absolutely critical for rigidity. How do these components actually differ between the two types? And what practical impact does that have on performance when you're really pushing the machine hard?
Right, the bed is truly the foundation. It has to absorb all those forces. For heavy-duty machines, it's massive. The research describes them as often being these single, heavily reinforced castings made from high-quality, dense cast iron.
Single casting.
Okay. Yeah, and they're often engineered with integrated rib structures, sometimes even double wall designs, specifically to maximize stability and resist heat distortion during long cuts.
Right, heat's a factor too.
Absolutely. The purpose is straightforward but vital.
Ah,
Achieve superior rigidity to soak up those huge cutting forces and, maybe even more importantly, effectively dampen vibration.
vibration damping. Yeah.
That is just non-negotiable for maintaining accuracy, especially with heavy workpieces and during aggressive material removal.
Yeah.
The guideways are engineered differently too. They're typically much wider, hardened. Sometimes they're dual guideways, or they even use hydrostatic lubrication systems to handle extreme loads really smoothly.
Hydrostatic. Wow.
Yeah, and many heavy-duty machines also use inclined guideways, maybe at a 30 or 45-degree angle. That helps with chip evacuation, getting the chips away from the cutting zone, but it also helps distribute the cutting forces more effectively, which again boosts that critical rigidity.
Right.
Standard lathes, well, as you'd expect, they have lighter structures. They might use standard cast iron or maybe welded steel fabrications, and they'll have narrower guideways, perhaps linear guides or medium-hardened ways.
More typical stuff.
Yeah, it provides sufficient rigidity for general tasks, for sure, but it simply couldn't cope with the immense forces you'd apply when, say, roughing a multi-ton forging. The standard machine is balancing rigidity with speed and cost, whereas the heavy-duty design, it's got this singular focus on maximum stability for extreme conditions.
Okay, so they're not just bigger versions, they're fundamentally engineered differently for that extreme performance envelope. Given that complexity and scale, though, is maintaining one of these heavy-duty machines just a scaled-up version of standard lathe maintenance, or is there more to it?
That raises a really important question, and the answer from the sources we looked at is definitively no. It's not just bigger. While sure there are overlapping principles, maintenance for heavy-duty lathes is significantly more rigorous and specialized. The sources detail specific requirements that are absolutely critical. For instance, the lubrication systems are far more complex.
More complex, how so?
Well, they need detailed checks and often require very specific lubricants for different components. You might need an extreme pressure grease for the axes, but then a special spindle oil for the spindle cylinder, for example. It's not one size fits all.
Gotcha.
Diligent air source management is vital. Failing to regularly drain water from air systems can lead to really costly rust issues inside pneumatic components.
Right, the basics become even more critical.
Exactly. And chip management becomes a major operational task, simply because of the sheer volume of material being removed. Letting chips pile up isn't just messy. It can actually cause system failures or damage guideway covers.
Makes sense.
You also need consistent checks of the hydraulic and pneumatic systems monitoring pressures, temperatures, filters. Given the forces involved, regularly checking and adjusting transmission chain clearances is crucial for maintaining accuracy over time.
Okay, lots of checks.
Yes. The electrical cabinets are typically larger, they draw more power, and they require meticulous cleaning and ventilation management to prevent overheating. Advanced coolant systems need constant monitoring concentration, filtration, and, maybe most critically, regular calibration and alignment checks are absolutely needed to maintain that precision under heavy load, year after year.
And I guess the people running them need more skills, too.
That's another point raised, yeah. These machines often demand more highly skilled operators, and frequently you'll need additional support equipment like overhead cranes simply to manage the sheer size and weight of the workpieces, or even the machine components themselves during maintenance tasks.
Wow, okay, that's a whole different level of commitment, isn't it, just to keep it running optimally. Let's shift gears then to the practical side, kind of the bottom line. When does investing in one of these heavy-duty machines stop being an, I don't know, extravagance and become a necessary investment? What are the key scenarios the source material points to?
Yeah, and this is where it gets really practical for decision-making. The research provides some pretty clear scenarios where a heavy-duty lathe isn't a luxury item, but actually an essential profitable tool. It truly boils down to aligning the machine's capabilities with the unrelenting demands of the specific jobs you're taking on.
Okay, so what's scenario one?
Firstly, it's if you are consistently working with large and heavy workpieces. That's the most obvious one.
Right.
The sources cite examples like parts exceeding, say, 2 meters in length, diameters over 400 millimeters, or weights going from hundreds of kilograms up to multiple tons.
Tons. Okay.
Yeah, think about manufacturing things like wind power main shafts, big industrial rollers, heavy-duty pipe fittings, or components for the oil and gas industry.
Yeah.
A standard lathe simply cannot physically handle that load safely or effectively. The structure isn't there.
Right. Physically can't do it. What's next?
Secondly, if your work requires high cutting force and power, this could be because you're dealing with really tough materials like high nickel alloys
Yeah.
or hardened steels, or maybe it involves aggressive roughing passes, taking really deep cuts or deep hole machining.
Ah, okay.
That superior torque we talked about, and the bed rigidity. They're indispensable for preventing tool chatter and maintaining accuracy under that kind of intense strain.
Makes sense. So, big parts, tough cuts. Anything else?
Thirdly, if you need continuous high-volume production of very robust parts, think industries like shipbuilding or power plant component manufacturing. They often require machinery that's engineered for high-intensity, long-duration operation with minimal downtime.
Built like a tank, basically.
Pretty much, yeah. The inherent robustness of a heavy-duty lathe is designed precisely for that kind of relentless production environment. They can take the punishment day in, day out.
Okay. Number 4.
Fourthly, if you are machining complex, high-value structural parts, this comes up a lot in aerospace or heavy machinery production. You might be working with intricate shapes or maybe large welded assemblies that need final machining.
Right. Expensive stuff you can't scrap?
Exactly. The enhanced stability and support provided by a heavy-duty machine are critical for achieving the required precision and ensuring reliability on these extremely expensive components. You need that confidence.
Okay, that covers a lot. Is there a 5th?
There's a final point the sources touch on. Even if your final machining tolerances aren't necessarily sub-micron, maybe they're a bit wider, but you need high process stability and dimensional consistency across many parts, especially during rough machining.
Ah, consistency during roughing.
Yes. The heavy-duty machine is just far more stable and predictable under those heavy roughing conditions than a standard machine might be. So you get better consistency from part to part even before finishing. What's really fascinating here is how these specific use cases really frame the heavy-duty machine not just as a piece of equipment, but as a fundamental, necessary cornerstone for profitability in these demanding sectors.
That really lays out the map clearly.
Yeah.
Yeah, it sounds like if you're dealing with materials that really fight back, or parts that weigh a ton, sometimes literally, or jobs that just demand that unwavering stability for aggressive, long-duration work, well, then the heavy-duty machine isn't just nice to have, it's the essential tool for the job.
Exactly.
And the standard machine, well, it remains the go-to for the smaller, general tasks where speed and precision on less challenging parts are really the priority.
Perfectly summarized. Grasping these core distinctions that we've pulled from the sources is absolutely vital for making an informed decision, for selecting the machine that genuinely matches your specific operational needs. It avoids costly mistakes.
Absolutely.
And, as you think about the future of manufacturing, and maybe your own capabilities, here's a final provocative thought, something to maybe mull over. Beyond the current applications we've discussed today, how might ongoing advancements in, say, material science or perhaps increasing levels of automation, how might those potentially reshape or further push the boundaries of what heavy-duty machining even means in the years ahead?